Yeah. Okay. Oh, I can do that. Oh, I can do it as well. Okay. Right. Yeah. Good afternoon, everyone. I'll just give a brief introduction to this webinar while people continue to join. Many thanks for everyone for attending. Today we've got two speakers, Dafni Sifnioti, who's from EDF, and Daphne is a senior manager of the Natural Hazards and Environment Research and Development team in EDF. She's been responsible for key assessments for EDF on external hazards and climate change. And over the last 3 years, Daphne's grown the team's capabilities. Daphne's background is on coastal geomorphology, coastal oceanography, marine climatology, and previously worked as a senior scientist for CFAS and a project manager for coastal monitoring programs in the UK and Greece. Now, Greece does sound a bit more appealing than Lowestoft, but anyway, Daphne is a fellow and chartered meteorologist of the Royal Met Soc and has over 10 years experience in the field. So just to go through the session, questions and answers, please put in the Q&A button at the top of you'll see at the top of Teams. Use the chat only for technical issues, please. There's any issues about getting in touch or logging on, or if you haven't got some of the functions working. I'll get the speakers to answer questions at the end of the talk, at the end of their presentations. If there's any generic ones, we can talk to, hopefully have time just before we close off at 1 o'clock. Daphne will be followed by Phil Sansom, who I'll introduce as he starts his presentation. In terms of where we are, please can you remain muted? The webinar is being recorded and the recording will be shared on YouTube. I've been informed, and there is an email there if you are having any technical issues. So first of all, I'd like to fire over to Daphne and look forward very much to her presentation. Daphne.
Thank you very much. I think I can now control the presentation. Can you see it in full screen though, just so I can confirm if you can see it full screen?
That looks good to me, yeah.
Okay, all right, because I see it with notes and stuff. All right. Okay, so let's make a start. Thank you for that introduction. So I'm just gonna explain today what we do in UK R&D for EDF and how we use the UKCP 18 and why. Thank you for describing that, so I don't have to do the awkward thing of explaining who I am. So thank you very much for that. And yes, Lowestoft is very different from the Greek beaches that I have monitored in the past. I can definitely agree to that. So this is a bit of the outline on how today's session is going to go. So I'm going to explain natural hazards and nuclear, the UK regulation and climate change, data, what our colleagues in EDF group do about climate change, what we do then for EDF UK R&D, and then also I'll just go briefly via a case study for air temperature. On the right-hand side, you can also see a map of our nuclear assets and where they are in the UK. They are in different stages of their lifetime, I can say. So some of them are even in planning session, others are currently getting constructed like HPC. And then, of course, we have the current fleet and the fleet that is in the defueling and decommissioning stage. So in terms of external and natural hazards, we have very clear definitions from the Office for Nuclear Regulation. So external hazards include both natural and man-made hazards that originate externally to our asset. That could be, for example, earthquakes or accidental aircraft crashes or even off-site chemical releases. So things that we may have very little or no control over the initiating event. And the natural hazards are a subset of this external hazards definition. And of course, there are the hazards that are due to natural processes. So these can be earthquakes, as I mentioned earlier, but of course, extreme weather and coastal flooding. And on the right-hand side, you can see the various guidances that we have from the ONR on what we consider external and natural hazards, and of course the safety principles that we have to follow. If we look into more now into the categories, if you like, under external hazards, and don't worry, I'm not going to read all of them in full detail. There are the ones that I mentioned, natural hazards, but you can see that climate change is not defined as a hazard on its own. So I would say it's all of these types, and of course, climate change where applicable that we have to consider. So if we look into the categories, you have flooding and hydrological, so things like sea level, rainfall, storm surges, seismic, meteorological, so air temperature, like the case study that I'm gonna explain later on. We have biological, so of course, can we combine marine ingress events with climate change? Geological, like coastal erosion, or even landslides, if we can combine them with climate change. Fire, of course, wildfires. We've all seen the wildfires in my home country in Greece for this year. Man-made, and then other activities, for example, space weather, meteorites, and other topics. Now, the UK regulation on climate change, so the ONR has produced a joint regulatory advice and guidance with other environmental agencies. So, for example, with the Environment Agency, or with SIPA and Natural Resources Wales, on what we should consider, if you like, on climate change, and what's the best practice, and of course include up-and-coming science. So for natural hazards, for a design basis, we need to consider the 1 in 10,000 year event, including reasonably foreseeable climate change over the lifetime of our facilities. So for nuclear assets, for example, the lifetime is about 60 to 80 years, which matches nicely, if you like, from the information that we have from UKCP 18. In general, we are considering the 84th percentile. And it depends how your data set looks to define that. We need to incorporate UKCP 18, so we usually do that with climate change adjustment factors. And then, of course, we need to periodically review our assessments, and the ONR guidance suggests that we have to do that once every 10 years. It's also expected from us that we need to have the right measures in place to ensure that we can be proactive for the various risks that we can identify. That also varies per location and, of course, per facilities. And then finally, we need to have an adaptive approach on climate change effects, and again, consider any uncertainties in either the data and our results, or of course, the measures that we take. And on the right-hand side, you can see the various guidances that have been produced by the ONR and other regulatory authorities. Now, why are we doing this? Of course, I don't think this comes as a surprise to anyone here on the call that the climate is changing. So a very nice infographic, if you like, from the state of the UK climate in 2022. I really like these graphs from the state of the UK climate. I find them very concise and very good to use to explain how the climate is changing. And of course, we can see that we had some very high temperatures in 2022, not to mention, of course, the heat waves that we had in July with records being broken with 35 or 40 degrees in London for those who were very likely to experience a heat wave in London last year. And then, of course, when we consider any changes in our climate in the past, we need to assess that to ensure that we can understand any risk in the future as well. And how do we do this? So, of course, we're talking here about the UKCP 18. So, as my title says, data is what we do almost every day in the team. We use climate models to ensure that we have the right assessments. Of course, we have the IPCC data sets, either from AR5 or AR6. And then, of course, you need to consider RCPs and the new SSPs from AR6. However, for our UK assessments, we are required to use UKCP 18 as the guidances that we have from our regulators. So we are not using IPCC AR6 data for our UK models, for our UK assessments. So for UKCP 18, as we mentioned, we need to use them to ensure that we have an assessment of the risk exposure to climate change. And then, of course, it's the most recent data that we have on climate models, and of course availability varies across parameters. But the key topic here that we have is that the UKCP 18 projects greater chance of hotter, drier summers and warmer, wetter winters. With the data, of course, comes uncertainty, which is another key challenge, if you like, for us to consider. And I'll leave all the difficult statistical explanation maybe to Philip, who is after me. And I'll ask you questions, Philip, as well, if I can. We usually have 4 main contributions to climate uncertainties. And of course, the application really guides the choices that we make for data, for models and scenarios that we need to use. But you have some understanding on uncertainties. So for example, emission uncertainties are really most important after 2050. Then we have to consider, of course, any input information for our models as well and how that will change. The initial condition uncertainties remain stationary. And then, of course, we need to consider that natural variability uncertainty is assumed also to remain stationary. And of course, as we go towards 2100, we can see that these uncertainties are even larger. And of course, we can, if we consider that and the aspect that we have to do the 1 in 10,000 year 10 levels assessments, that of course really makes it a bit more intriguing, let's say, on how we do our assessments. Now, what do we do as a business? So EDF Group, back in 1990, our scientific advisory board highlighted in a relevant session that we need to consider climate change and to examine any possible consequences that we may have as a business. And of course, that means that within EDF Group, we have climate and environment expertise driven by nuclear safety for about 30 plus years. And we have also realized too that it does impact various parts of the business, but in general, all parts of the business can be impacted. So it could be from demand, production, generation, safety, health, our land properties. So we need to consider all that. So then, of course, we need to, as I said earlier, we need to identify the present climate risk, the future climate risk. And then, of course, we need to ensure that we can adapt our assets and ensure that they are resilient. So it really matters on the hazard that you're talking about, the vulnerability that you have from this hazard, the exposure, and then, of course, if you consider all of the above, the risk. Some examples are also provided here. So heat waves, multi-hazards, and sea level rise, as well as flooding, of course, are things that we need to consider in a more holistic point of view for our assessments. Continuing with EDF Group and climate change, so back in 2003, we also had a very big heat wave that broke many records in France, about 70 out of 180 Météo France weather stations. There was also the challenge that we have riverine stations, so that increased the river water temperature, that we couldn't use or prohibited the use of nuclear power and cooling systems. But that led, of course, into developing a climate adaptation plan in EDF Group to ensure that we have an R&D program to do the right climate change assessments that we need. And then that also led to building our own EDF group internal climate service in 2014. Now, of course, in the UK, so that brings us to my team. We haven't been as long as our colleagues have in France. So EDF UK R&D was established almost 10 years ago. So we have been working for several years now with our colleagues in the various nuclear assets and business units on different assessments for extremes and climate change. Some different examples here you can see. For the design for HPC and Sizewell-C, we've done assessments using UKCP 18 on future heat waves or extreme higher temperatures and extreme sea surface temperature. This was mostly with UKCP 09 because UKCP 18 doesn't have the temporal resolution that we need for sea surface temperature, even though I think recently the monthly SST was made available. For safety cases, we also look into sea level rise, storm surges, rainfall, wind, again, temperature and lightning. And then, of course, I mentioned already the expertise that we have in the team on climate change scenarios, climate adaptation, and marine ingress. So the way that we work is, yes, in the team, we have, if you like, the expertise to do the assessments, but we don't do things on our own. We have very good relationships with our colleagues in the various EDF UK business units that, of course, have a lot of expertise and exposure and vulnerability. They have the assets knowledge, which is, of course, very important to us to ensure that we do the right assessments, but we also provide the right information that they will need for building the safety cases or also for the designs. And that, of course, will help us establish an adaptation plan and ensure that we have business continuity. So using UKCP 18, the way that we usually think about things is what's the vulnerability of our site to a specific climate-related hazard? Can we identify any evidence on climate trends, the availability of data sets? If we can identify also observational data sets nearby to our site, so for example, using the Met Office weather stations, because we need these long-term records to ensure that we can do the best statistical analysis that we can do. We need to check, of course, if we have the right projection data sets from UKCP 18 and other sources. And then we look more into any increases in frequency of and severity of high temperature or heat waves or other related hazards. And then for flooding risk, we consider most of the different sources, fluvial, coastal. As you would see the map that I showed earlier, most of our sites are in the coast. The guidance that I mentioned earlier, as I said, requires us, there you go, requires us to estimate the 1 in 10,000 year event using extreme value analysis or EVA, which I know Philip is going to say all about that. And we need to characterize the future extremes by estimating the extreme events in the past, and then also have an addition of a climate change adjustment factor, which is also provided by applying the EVA on UKCP 18 data. So it really depends, though, how we do this on the hazard that we are assessing. So higher quantiles are considered for UKCP 18 coastal flooding projections because of the larger uncertainty in longer horizons. But also 50% quantile is conservative for higher temperatures at the RCM for UKCP 18, as they are considered to have a hot bias if we compare it to other climate models. And then we can move on to the case study. So the case study that I wanted to bring here is the UK air temperature. This year, we have basically reassessed our air temperature analysis for all of our sites, at least for present day, and we are moving towards completing the future as well, future assessments. And the way that we've done this is because we wanted everyone to be aligned in their analysis and their assessments, and that everyone has updated results as well. So we looked into air temperature. So nuclear operation, which is our current fleet, needs guidance and data analysis to understand the risk over the next decades as they progress towards decommissioning and defueling. New nuclear build. So of course, this is more for the design. So here we're talking about the HVAC to ensure that it remains resilient for about a century. And then for defueling and decommissioning sites to anticipate the long-term climate risk. And as I said earlier, the way that we do this is we try and find the appropriate observations to ensure that we do the present day analysis properly. We pre-process and quality check the observations. We pick the right statistical approach to get the extremes. We select the climate data. So from UKCP 18, for example, is the RCM or the CPM. And then we pre-process the climate data, and then again apply the statistical approach to ensure we get the climate change adjustment factor. So all of this works together, but it's clear that there are different perspectives depending on who you do the assessment for. And then, of course, it all needs to be summarized, if you like, in a technical report, and then it will help the business to make the right decisions based on science. So one of the reports that we did a couple of years ago, it was about comparing the UKCP 18 data and other global climate model outputs. So we were looking into the various models provided by UKCP 18 and mostly focusing on the GCM, so the global climate model. So we weren't necessarily looking into doing EVA maps, if you like. I was mostly doing spatial maps of daily means and daily maximum air temperatures across the UK, just to see how models were changing across the different timelines and across the different locations that we were interested in the UK. And then, of course, we did a bit of a local analysis as well for 2 stations, and that was as part of our new nuclear build, so with Hinkley Point C and Sizewell C. And then we were able to identify further comments on how things varied across the different models and what could be of interest to our business. And I think that's where I'll close for today. I just wanted to give a brief example for what we do in EDF UK R&D. I should say, of course, we collaborate with the Met Office a lot. So they get too often, they may say a lot of questions from my team, but we have very good relationships with the Met Office. And of course, we depend on the data that they provide to us for us to do our assessments for our sites. Hope that was okay. Happy to take any questions.
Fantastic, Daphne. Thank you very much. There's a Q&A is coming in the Q&A tab. Let me just.
I'll stop presenting at the same time.
Yeah, I'll just read these out. There's one here from Farida Shaban. Which RCP scenario do you usually use in your analysis? Is RCP 8.5 too pessimistic?
We use 8.5 because it will give us the worst case scenario. And that's the key reason why we use it, if you like. So it's the RCP 8.5, and usually for most of our assessments until so far, we have been using the 12-kilometer data set, but we are now trying to explore the continuous data set from the 2.2 kilometer for specific hazards. And of course, it helps a lot for the 2.2, especially for rainfall, but it's the RCP 8.5.
And we've got a few minutes yet. So Caroline Sussons asked, what is the basis for assessing credible maximum climate change scenarios and climate change scenarios beyond 2100, given UKCP 18 only goes to 2100?
Yes. That's something that we have a lot of discussions internally for credible maximum, but also for how it changes per hazard and how far in the future we want to do the assessment for. So I don't have a very clear answer on this because this is work that we will be looking into for next year, if you like. So check with me again next year on how we're going to actually do this. But in terms of the time horizons, yes, the longer you go into the future, the further away you go into the future, we realize that the uncertainties also grow. So it's very difficult for us to be very, how can I say this? Sure, certain that what we provide is as certain as it can be because of the problems that we have, if you like, with the models. But it is something that we are going to think about this more next year.
And I'm just taking Chair's prerogative here. You know, EDF is global company.
Yes.
So how does the work that you're carrying out within a UK context fit in with what's being carried out by your colleagues elsewhere? Is it, and can you make any comments on whether they have the data capabilities that UKCP 18 provides?
Yes, so usually our colleagues in a group, when they do the assessments for the various locations, they use, now they use AR6, MIP6 data sets, and they downscale them and bias correct them. So they don't have, if you like, a UKCP 18 data set, because that's specific to UK.
Yeah.
But that's how they do the assessments. The key thing here is that we try and be aligned as much as we can with what our colleagues are doing in France in terms of the science and the technical assessment. So if there is a new methodology used in France, we try and see if we can use it with UKCP 18 data in the UK and see how that helps. And it's the other way around. We have PhD students, for example, who are doing a very good job. And what they do in the UK, if that can be applied in France or elsewhere.
Okay, and just go. Oh, sorry, new post coming in. Just pick up a question here from Katie Hodge. For risk assessment for a given site, what resolution data do they use? 12, 5,
Yes.
or 2.2?
12. So
Okay.
it depends on the hazard, but we have used mostly the 12 kilometer because up to March, maybe this year, the 2.2 kilometer wasn't a continuous data set. So we really prefer to have continuous data sets for our assessments. But now we're trying to explore the 2.2 kilometer and how we can use that for rainfall assessments as well.
And okay, there's some, yeah, just to please use the Q&A function, not the chat function, please, for asking questions. I know there's some now coming into the meeting chat, but we'll try and follow those up afterwards. Just, you mentioned as well, Daphne, that for sea surface temperature in particular, the resolution wasn't good enough. Do you want to say something about the current resolution and what you think a suitable resolution would be?
So the sea surface temperature is an interesting one. I've discussed this before with the Met Office. So I think when we moved from UKCP 09 to UKCP 18, we didn't actually do the sea surface temperature models. I know now that they exist in the Met Office's vaults, but I think we now have the monthly SST is available from UKCP 18. I haven't checked it yet, but I think I saw an update on that one that it's now available. However, for us to actually do assessments in the same way as we do for air temperature, we need ideally sub-daily data. So it's very difficult for us to use monthly information other than to produce, for example, monthly climatologies, for example, and how SST will change in the future to do with the extremes. So if we are going to do assessments for SST, we're going to use MIP6 probably, but that also brings challenges as well. Okay,
thank you very much. Look, sorry I can't go through it. There's a real good chunk of questions come through here, so sorry I can't, time's not permitting to go through all of those. Daphne, if I can ask you if you got a chance just to respond to anyone individually, that'd be fantastic.
Yep, I'll have a look.
So just like to now move on to our next speaker, Philip Sansom from the Met Office. He's looking at extreme value analysis of meteorological hazards in the changing climate. Phil's the senior statistical scientist in the Industry Science and Consultancy team within the Met Office, and he works closely with industrial partners across multiple sectors, including water and energy. And the Phil's been developing statistical modelling approaches to help better understand extreme events and the impact of weather and climate on operations and infrastructure. So it's a good follow on from where we have been with Daphne. So Phil, if I can hand over to you. And again, just to reiterate, you can put the questions in the Q&A, please. Thank you.
Thanks, David.
Sorry, I'm trying to get the slides on, and they're not wanting to come back on. Give me a sec.
Okay, so whilst Tali works on the slides, it would be a tall order to go into detail on EVA in just 15 minutes. So today I'm really going to follow on from Daphne by talking through some of the available UKCP 18 data sets with respect to their application to EVA type problems, extreme value analysis, and what some of their strengths are, and where they may or be more or less suitable depending on your application. So that's plan for today. I'll be focusing mostly on land variables because that's what I do most in my work. So I'm not the right person to speak to Daphne's want for sea surface data.
Sorry,
But
Philip, could you try sharing yourself? Because my sharing capability is not wanting to do any kind of sharing right now.
Okay, just give me a second.
Does Daphne need to stop sharing, or is that the issue?
I have stopped sharing.
Okay, thank you.
Yeah.
Thank.
I'm just going to reset my screen a minute because otherwise I'm told things look very strange if I just share my screen by default. Oh.
Brilliant. Okay.
I think
There
I
we go.
managed. Thank you.
Yeah.
You can take control now. Thank you very much.
Okay, so yeah, as I said, I'm not going to go into too much detail on EVA itself. I'll give a few indications of how we can do specific things using UKCP, but I'm mostly going to focus on the data today. There we go. So the UKCP 18 land projections contain a number of data sets that are useful for extreme value type problems. In particular, the probabilistic projections of climate extremes are specifically designed for this purpose, but I'll talk through some of the other ones as well. And I've given links to the major reports and things where you can find more details about each of these as we go along. So some of the things Daphne already mentioned, these that we want to consider when we're thinking about these sort of extreme value assessments. The spatial resolution we've talked about a little bit. Essentially, if you're using a global model with only, say, 60-kilometer resolution, that's essentially averaging over that 60 kilometers. So the very local extremes, what you'd experience in a particular point, are going to get a little bit blurred out. So spatial resolution is definitely a consideration. In general, the higher the better. Temporal resolution, again, Daphne touched on, we often need daily or sub-daily. Daily max or min is sufficient for many applications, but sometimes we actually need hourly data from each variable. Coherence over space and time and between variables if we want to compare. Some of the data sets here, traditional climate model outputs offer complete coherence. Others, depending on their purpose, may not, so I'll highlight that where we go along. Availability of variables. Some data sets I'm going to talk about have more variables than others. And Daphne already touched on sources of uncertainty that contribute when we're thinking about extreme value analysis or anything climate change. One of the biggest is climate model uncertainty. So different climate models give different projections. Also emissions uncertainty, scenario uncertainty, however we want to call it. Essentially the uncertainty about how many greenhouse gases we're going to keep pumping out and what their response is. And then natural variability in the climate itself. Essentially, we want to use the longest records we can because we're looking at extreme events, which by their very nature are rare, and we're trying to extrapolate beyond them. In many cases, all the way out to a 1 in 10,000 year event in the case of the nuclear industry. So we want as much data as possible to try and pin down the natural variability as well. So the first stop in UKCP 18 for an extreme value problem that I'd recommend would be the probabilistic projection of climate extremes, because they're designed for exactly that purpose. They're an extension of the probabilistic projections, which I'll talk a bit more about in a minute, augmented already with statistical extreme value theory. So we've fitted extreme value models to a lot of climate projections to give the best overview we can. And this data set has the form of pre-made return levels, 20, 50 and 100-year return levels, and you've got the individual percentiles of uncertainty on those, which you can see examples of plotted on the right here. And this covers 1960 to 2100 with seasonal time steps. So you can look at the traditional meteorological seasons for each year down to 25K resolution. And this covers daily maximum and I think minimum temperature, I think daily precipitation and daily 5-day accumulated precipitation. So these are some of the most commonly analysed variables already there in a form that you can use straight away. And these are also available for several different emission scenarios. So we've got most of those uncertainty factors covered here. So the good things about this data set, we've got the broadest possible assessment of known uncertainties here, because we've incorporated multiple models, we've got multiple scenarios, we've already done the EVA analysis based on peer-reviewed methods. And unlike some of the other UKCP products, this is done in terms of absolute values. So you're getting the actual temperature we're expecting in a particular year, and it's already bias corrected, so you don't have to worry about any of that. So there's a lot of work been done here. The limitations, we've only got limited variables and return periods out to 100 years. Now, for many problems, that's sufficient. For the nuclear problem, for nuclear assessments, as Daphne mentioned, that's not nearly enough. We've only got seasons available. Now, again, for many problems, that's fine, because you're looking at daily max within summer or daily max within autumn. That's fine for many things. If you need to be more fine-grained down to monthly, then this isn't down to particular months or exact times. This isn't going to cover it. And while you can compare different locations using this data set, you can't use it to look at the probability of simultaneous extremes, so compound hazards, which people are increasingly interested in. But overall, this is a really useful data set that I would recommend as the first stop for EVA for climate hazards in the UK. The probabilistic projections of extremes build on the probabilistic projections themselves, and these are based on outcomes from over 350 climate model simulations combined in a Bayesian probability framework to give us a really broad assessment of the known modelling uncertainties. And this covers the same time period and spatial domain as the probabilistic projections of extremes, so 1960 to 2100 at 25-kilometre resolution over the UK. It's also available pre-aggregated to various higher areas. But the advantage we've got in this data set, we've got a lot more variables available. Monthly, seasonal, decadal averages of temperature, precipitation, humidity, pressure, radiation, cloud cover, and also global mean surface temperature, because it's derived from some global climate models as well. So that's useful. I'll outline how for some other applications later. And again, we've got all the emission scenarios, all the common emission scenarios here. So we can look at emissions uncertainty as well. And these are provided as either 3,000 samples at each location and time you can analyze yourself, or as pre-made percentiles of the PDF or CDF from those samples at each location and time. Again, you've got examples of what that looks like on the right-hand side here. So the advantages of this data set, again, really broad assessment of known uncertainties, multiple emission scenarios available, and more variables than the probabilistic projections of climate extremes. But we're limited by monthly resolution for most variables. So although we've got daily, probably max temperature within a month there, the other variables are just monthly averages, which is a bit limiting. And again, it's temporally but not spatially coherent. So we can look at compare variables at sites over time, but we can't aggregate over locations here. The analysis is done at each 25k grid box separately. The other caveat on that is there's no wind data in here, which is often of use. But it's not really intended for extreme value analysis. That's why it was extended to the projections of climate extremes. However, you can use it for EVA because we've got it's in the form of these 3,000 samples. So you could think about getting shorter return periods, maybe 1 in 50 years, maybe 1 in 100 years from the 3,000 samples before you start to run out of samples above that threshold. So you can easily derive the return levels from the quantiles, the samples, and then you could assess the uncertainty by resampling those samples. So you can use this for EVA, not really what it's intended for, but if the variables are useful to you and not available in the climate extremes data, then this can be used for EVA type applications. So moving on to some of the more traditional products from UKCP 18. The UKCP 18 global projections have a resolution of about 60 kilometers over the UK. And this is made up of a 15-member perturbed physics ensemble, so 15 different versions of our Met Office model, and 13 members from the CMIT 5 multi-model ensemble to help look at model uncertainties as well. And this covers 1900 to 2100 with daily resolution, but it's only available for RCP 8.5, though that's very often what we find is used for planning purposes because, as Daphne says, it's a reasonable worst case scenario at the moment. You've got more variables available here, daily and monthly, temperature, means, mins, max, precip, wind, pressure, most of the usual variables available. So the big advantage of this data set is you've got the multi-model ensemble included as well. It's all there in one place. You don't have to go downloading multiple models from multiple archives. It's all there in one place. You've got global coverage if you're not just interested in the UK. And you've got the extended historical time period all the way from 1900. And you've also now, because these are traditional climate model simulations, you've got full temporal, spatial and variable coherence. So you can aggregate over any areas you want, and you can compare over space and time and compare variables to look at simultaneous hazards. The downside to this data set is you've got the low spatial resolution problem. So it's not going to drill down to the exact conditions at a particular site. So maybe not so useful for, say, nuclear applications where you're really interested in the effect on your exact location. But for many applications, say gas, water demand due to temperature, the heating, where you can cope with a few hotspots within an area, hotspots of demand within an area due to very low temperatures, say, you're more interested in the average over an area. This is potentially a good option. Single emission scenario, again, not too much of a limitation because it's a reasonable worst case scenario. And obviously no specific analysis of extremes here, so you'd have to apply statistical EVA methods to the climate model data, potentially after bias correction. The regional projections in UKCP 18 go one step further in sort of localizing in resolution. That we're down to 12-kilometer resolution here. So this is really drilling down into those local effects a lot more. And this is a 12-member perturbed physics ensemble, so it's different versions of driven by different versions of the Met Office climate model, and then downscaled using a regional climate model from the global projections. This only covers 1981 to 2080, so not quite as long a time period as the global projections, but useful for most planning horizons and for comparison with OBS since the satellite era anyway. And this covers the whole of the UK and Europe as well. Only a single emission scenario, but again, reasonable worst case scenario, all the usual variables available. So the big advantage of this over the global data set is the higher spatial resolution, so we get better representation of local extremes. So again, potentially useful for single sites such as nuclear applications, definitely good for sort of demand-based applications, gas, etc., electricity. And then again, we've got this full spatial temporal variable coherence, so we can analyze anything we want using this data set. Downsides here, there's no multi-model ensemble included, so we're missing that model uncertainty component, but you can augment this data with similar regional climate model downscaling experiments from the Eurocordex dataset, which basically takes the CMIP5 models and downscales them in the same way to basically roughly the same resolution. So very comparable. Single emission scenario we've talked about, and again, have to apply statistical methods after bias correction to do your EVA. But much better representation of extremes here, local extremes. Now, drilling all the way down, Daphne briefly touched on this. The big advance in UKCP 18 was the inclusion of the local projections down to 2.2 kilometer resolution. So this is again a 12-member ensemble of the Met Office, of a single Met Office, of the Met Office model driven by the UKCP 18 global projections, but using a very high resolution model only over the UK. Now, the advantage of going down to this resolution is it's what's called a convection permitting model. So it's much better at simulating intense summer rainfall events. But it also corrects a lot of small biases in other variables compared to the regional projections. The other big advantage of this data set is that you've got hourly temperature, wind and precipitation data available. So that really addresses the requirements for some assessments for sub-daily data that Daphne mentioned. The other variable we have out of here is lightning, coming again from that convective simulating aspect. So the big advantage here is the high resolution. It's going to give a much better representation of local extremes when you're looking at conditions at a single site like a nuclear installation, and you can see that difference compared to the regional projections. So for really site-specific applications, this is definitely a good data set to look at. Again, especially with things like nuclear installations, which tend to be on the coast, you've got that best chance of getting data that's representative of the conditions on land but close to the coast and without being affected by nearby orography, hills, etc., that might be included in the regional data sets, and you get that smoothing effect. Hourly data is a big plus, and the convection permitting model, it gives much better simulations of summer rainfall, as I mentioned, reduced biases. Again, the main downside here is the lack of the multi-model ensemble to explore climate model uncertainty, but I can say a little bit about some ways we can get around that in the next slides. So the UKCP 18 local and regional, lots of information about local extremes when we need to get at longer return periods than the climate extremes dataset allows. Can require careful site selection. It's not always the best idea just to choose the grid box containing the site you're interested in. If that site happens to have a greater percentage of sea or of hills in it, when your site is actually down at the bottom, at the foot of the hills, you might actually be better off choosing the next grid box over, say, where it's better representation of land conditions or you're not affected by hills. Obviously, this requires careful verification against OBS, etc., to make sure that you are actually getting the best representation, but it's worth highlighting those issues. The primary limitations of these data sets, as I've said, is single emission scenario and single climate model. So we don't have that multi-model uncertainty aspect. So one of the ways we can overcome that is to combine the local or regional projections with the probabilistic projections. We do that by, rather than considering climate change as a function of time, we can model it as a function of global mean surface temperature and how that evolves. And the estimates of local sensitivity to change in GMST will be dominated usually by evidence from the observations. So the effect of climate model uncertainty is very limited. Any multi-model assessment you did would be very much dominated at the local scale by what you're getting from the OBS. The caveat on that is for some variables, the signal may not have emerged yet, so you will be more reliant on the estimates from the models. But then we can use the UKCP 18 probabilistic projections of GMST, since we're now modelling as a function of GMST, not time, to project return levels as a function of global mean surface temperature. And the probabilistic projections of GMST do include model uncertainty and are available for multiple emission scenarios. So we're back to covering all the major sources of uncertainty without too much compromise. And then you can essentially use the local and regional projections to increase the sample size over the OBS, as well as providing an outlook into the future, again, after appropriate bias correction and possibly pre-processing. So yeah, that's an overview of the available UKCP 18 land products and how they can be used for EVA type applications and where they may or may not be more useful.
Okay, Phil, thanks off that. We've got time for a number of questions. First of all, just starting off with Sean Wilkinson. Sean said that he's a bit confused about the probabilistic projections not being useful for directly doing EVA analysis, but haven't you done that already to get the return periods?
So the probabilistic projections of climate extremes have already done the EVA, not directly on the probabilistic projections, but on the underlying 350 odd models that contributed to the probabilistic projections. The probabilistic projections themselves give you, in the form I usually use it, 3,000 samples of the conditions at the time and location you're interested in. So they cover the broadest range of outcomes that we believe are plausible. But from that, you would have to estimate the quantile you're interested in to get that corresponds to the return level you're interested in, which is as simple as just taking the quantile of those 3,000 samples that corresponds to your return period. But that doesn't then get you uncertainty. For that, you'd have to resample again. So it's not really what they're designed for. When we produce the climate extremes, we're applying statistical methods directly to the simulation data, not just to those samples.
Okay, thank you. Just picking up a question from Farida, or clarification point from Farida Shaban. Is there any documentation on the probabilistic projections, on how the probabilistic projections were bias corrected? I do believe that's all on the UKCP site.
I do believe it's all in the reports. Yes.
Yeah. I'm quite interested. There's quite a lot of comments here about bias correction. I have my own views on that, and the amount of effort that can be undertaken to bias correct models to get them to fit a particular view, I suppose. But it depends on what is required in the end use here, and how the data and the scenarios and the analysis of impacts using UKCP 18 are going to be used by decision makers. And I think that's all part of the cascade of uncertainty that flows down from the models right the way through to how results are interpreted and then put into operational practice as well. So I think there's a good discussion here about bias correction, whether it's always applicable, not always, whether it's gives extra benefit sometimes. But it'd be interesting to get wider discussion going on that, maybe at a later date, about bias correction.
Yep.
Katie Hodge. Phil, can you comment on which UKCP projections, local, regional, and probabilistic, have and haven't been bias corrected? There's another one about bias correction. So if you're using the change fields, if you're just looking at a future minus a present to give you a change in temperature or precip or whatever, you don't need to bias correct. If you get into more detailed analysis, but then from my perspective, one would probably have to question why you'd be doing such detailed analysis, especially when those data are going to be put through a wider cascade of uncertainty and that decision maker and interpretation as well. So, but anyway, I'll let you comment on that question, Phil, as I keep rambling on.
I think you've more or less covered it in some sense. The local, regional, and global are provided as raw data, so those have not been bias corrected. There is some guidance available. I can't remember if I've linked to it in any of the URLs I've given, but there is a document giving some guidance on bias correction of UKCP 18 data. Again, that's one of the great things about having the climate extremes product available. That's been done for you to the best of our ability.
Yeah, and then on that bias correction as well, just if a model performs well compared to the current observations and whatever analysis and whatever parameters you use to look at that, doesn't mean it's going to perform well in the future as well. And that's a fundamental point here that needs to be addressed, because a model can be over constrained, especially if it's a regional model which has been constrained by driving GCMs. So you've got all that uncertainty as well to factor in before one gets a bit too into the detail about and the nuances about whether or not one should bias correct data. Yeah.
If a model clearly performs poorly, then you've definitely got to be suspicious of it. If a model appears to perform well, you can't just accept that it's going to continue to perform well in the future.
Yeah. Okay. With that, Bill, we better leave that as we move on to the final stages. Just to, Silali, have you got the final slide? 25th of January. We have to go right to the fine. There you go. So the next webinar, 25th of January, because we can't have one over the Christmas break. Well, we could, but I don't think it would. I might get in the way of the mince pies and what have you. Anyway, Hannah Giddings from UKGBC. What's UKGBC? I don't know what UKGBC is. I'll have to get up to speed on that. And then I get Jennifer Pereira from the Met Office looking at storm guidance. Green Building Council. I'm having a stab at it. There you go. That was a good guess. And Katie's that means Katie must be from the Green Building Council. There you go. Anyway, so I look forward to seeing you all next time around. Remember, the recordings will be shared. And please do distribute the links and the invites as well to colleagues around, your direct colleagues with whom you work with, but also others in your wider network as well. So can I thank Daphne and Phil for the presentations, the UKCP team for all their organisation and getting me in the right place at the right time. And yeah, thank you very much for attending and all the Q&As that we've had as well. So brilliant. Thank you very much.
Thank you all.
Thank you.
Cheers. Bye-bye.